Yeah, feel free to get started.
Symbolic execution. So we'll start with some announcements.
Yeah, sorry. So Boiler CTF is tomorrow. We haven't announced this because we kind of just remembered. But Boiler CTF, that's run by Purdue. So we kind of have to play. That's tomorrow at 5, starting at 5 p.m. We'll announce more details on Discord, and but we'll most likely be meeting in person to do it. And lastly, shirts are the form is still open, because we haven't yet finished ordering logistics, but you have the form could close any moment. So if you haven't yet, fill it out to order a shirt.
Meeting flag. Yeah, this is a good meme if you can find it online. We'll talk about state explosion later, but yeah. Perfect. Okay, so yes, before we sort of get into Angr and symbolic execution and stuff, I wanted to start with some theory. So I guess the thing that symbolic execution is based on theoretically is SMT solvers, and an SMT solver is like a more general form of a SAC solver. So SAC solver basically solves or it takes some Boolean formula like the one that you see. So like not P or Q or R and P or not Q or not R. And it can do two things. One, it can tell you, is this formula satisfiable? Meaning, can you find values for your variables that will make the whole thing true? And then second, if it is satisfiable, it can give you a set of values that will make it true. So I guess for a formula like this one, you can do it by hand, Shorter's table or something. But if you have a lot more variables, you can imagine it's going to get very complicated. In the general case, satisfiability is actually NP complete, so it is a very hard problem. In some sense, it's basically the best thing you can do is to draw a truth table. It's exponential. But that's in theory land. In practice, there are actually many problems, even with lots of variables, that are solvable in like a reasonable amount of time. And it's the same for SMT solvers. So with an SMT solver, you have more than just Boolean operations. So with the SAC solver, all you can do is your ands, your ors, your nots, stuff like that. An SMT solver gives you stuff like addition, subtraction, real numbers, integers. All of that depends on this thing that you call a theory, which is a system of doing operations. So you could have, for example, a theory of integers that tells you how do you do addition, subtraction, multiplication, and division with integers. And then you can have your SMT solver, you can give it a formula involving those operations, and it will solve the same problem. It will tell you, is this formula satisfiable? Can I find values for my integers that will make the whole thing true? So any questions so far? No? Okay. Yeah, so theories, you have integers. So that's, mathematical integers behave as you would expect them to. You have this thing called bit vectors. So this is kind of what makes theories important. If you have, let's say, variables in a C program, they don't actually behave like integers. Even though you can do the same operations like addition and subtraction and so on, they have different behaviors. It's a different theory. It's a different way of interpreting the same operations. So you can have things like overflow, for example, which you don't have with regular integers. Like you can, let's say you have like 32-bit integers. If you add like the maximum possible value, you add it to itself, you're going to get overflow. And yeah.
So like SMT solvers then are trying to solve this like system of equations of different formulas.
Yes, so they are solving a system of equation, system of constraints where the formulas are written using one of these theories.
Okay.
So you may have formulas written using integers and operations on integers, formulas written using real numbers, operations on real numbers. And I guess the difference between like IEEE floats and real numbers is sort of the same as the difference between bit vectors and integers. There's some real numbers that you actually cannot represent with IEEE, and the SMT solver needs to respect those semantics. So that's where theories come in. Arrays are an interesting theory. They give you a model for state. You can load and store stuff at different indices. I mean, I guess big picture view is that a theory is a way to interpret operations and interpret variables. So you can interpret variables as integers and operations in terms of integers. You can interpret them as bit vectors and so on. An interesting theory is on interpret functions. So this is like, I guess, the most general theory where you have, in this theory, you have functions, and all you know about those functions is that they're pure functions. So an input always produces the same output. You know nothing else at all about what those functions do. All you know is that if I give it x, it will give me the same value wherever I give it x. So for instance, you could have something like you could have a constraint like, let's say, f of x equals f of y, and f is an interpreter. You can conclude from there that x must equal y, knowing nothing else about the function. Because you don't know what that function does. All you know is that same input, same output. So I guess in more practical terms, there's a library called Z3. Z3 is, I think, written in C++. There's bindings for basically every popular language. Python is very popular. There's SIGPwny. You can install it from the script. So this maybe gives you sort of an example of what you might use a library like Z3 for. In this case, you've got an array and there's all kinds of constraints. And so question, what theory would you want to use for the values in the array? Would you use reals, IEEE floats, bit vectors, integers? So imagine this is a C program. Yeah, pretend that this is a C program. What sort of type would you give to the values in the array? Yeah,
bit vectors. Overflows and C++.
They are bit vectors, but the semantics, right?
Yes.
So IEEE floats are technically vectors of bits, but operations have different semantics, right? If you have the same vector of bits, interpret it as a bit vector, it will give you some kind of integer. Interpret as an IEEE float, it gives you a different number. And you do addition with bit vectors, you have some way of doing some kind of carry and stuff. Adding IEEE floats is much more complicated. So it's different. The bits are going to get manipulated differently. So in this case, it's probably best to use IEEE floats. Yeah, so I guess I alluded to this a little bit. Z3 has data types, calls them SARPs. So they are basically going to correspond to the theories that you use. There's integers, bit vectors, reals, arrays, IEEE floats. Yeah. As far as operations, you have, of course, SMT is a generalization of satisfiability. So it can do everything satisfiability can. So in particular, all of your logical operations are still completely fine. So your AND, OR, NOT, implies, there's an if. Yeah, any sort of logical operation. Depending on the theory that you use, you get stuff like addition, subtraction, multiplication, division. You can do inequalities. Again, all of this, depends on the theory. You cannot like add to arrays. That's not a meaningful operation. You can add integers, bit vectors, and so on. And when you are dealing with bit vectors, you can also do bitwise operations. Again, like if you have an integer, it doesn't make sense to do any bitwise operations in an integer. There's no bits there. And using these variables and stuff, you can construct constraints. So constraint is something that's going to give you like a true or false value. It might be something like x equals 5 or x plus y is less than 10 or something like that. And what Z3 will try to do is it will try to give you what it calls a model, which is a assignment of values to all of your variables that satisfies all the constraints. Variables is in quotes here because I'm I guess calling them variables, since that's what you use them as in your program. They are technically not variables. They are constants that you don't know the value. Like with Z3, once you declare a variable, its value never changes. It has only one value throughout the program. It can't have two values at the same time. I think actually that like Z3 has this sort of funny Lisp style API. There, the way you create a variable is declare const, which is maybe a little bit more evocative of what it's actually doing. And if you want to use Z3, the Python API, that website is very good for like just telling you how to create variables that constraints operations and so forth. I think we have an example from that. Yeah.
So this model, is this sort of a naive assignment to the variables to just like fill in the SMT table, or is there a way that models are adjusted to cover code paths or something to make it a little bit faster?
Okay, so right now we aren't even talking about symbolic execution, so there is no code.
Oh, okay.
We just have a set of constraints, and a model is something that satisfies all of those constraints. So like, let's say you have just one constraint with integers that's x plus y is less than 12. There's a lot of different models you could have, but one is like x is 1 and y is 2. That's an example of a model. And okay, so yeah, this is essentially how you would solve a set of constraints. So x plus y equals 12 is one constraint, x less than y is another constraint. We are assuming that x and y are integers, so no overflow, nothing strange going on like that. So so you would start by declaring variables. Again, they are once you declare them, the value is fixed. You don't know where it is. They will try to find that for you, but you can't have x equal to 5 in one constraint and 10 in a different. In that sense, it's exactly like how variables work in math. Like you can't have the same variable taking different values in different equations. A solver is the object that solves constraints for you. So you create an instance of that object and you add your two constraints. And I guess with like Python operator overloading and stuff, you can use usual Python operators and everything works. So check will do a satisfiability check. It will tell you, is there a set of values that satisfies all of these constraints? In this case, there is. It says nothing about how many there are. I mean, there could be 1, a million, infinite. All it tells you is there at least one. It will tell you SAG, meaning satisfiable, if constraints are satisfiable. And then you can ask it for a model. Again, this is one of many solutions that the constraints could have. I think it's deterministic in the sense that you give it the same constraints and it will give you the same model. I mean, not like no, okay, yeah. So you could, I guess maybe like a seed or something, but yeah. But I mean, if you want all the solutions, that's not something Z3 can do for you necessarily. If you want one of them, then you can do that. If you want all of them, you need more interesting stuff that you need to add. And like figuring out, if the set of solutions finite or something. Do you have a question? Okay, so I mean Z3 is not just good for doing stuff you can do by hand. Like this is the n queens problem. What's going on here is you have 8 queens on a chessboard, and you want to place them so that no 2 queens attack each other. So you can't have 2 queens in the same row, column, or same diagonal. Probably to do this by hand is not easy, at least it's time consuming. But this is very easy with CP. So, so the way you're going to do this is, again, this is from that website, this example. You know that all the queens must be in different rows. You can't have 2 queens in the same row. So all you need to figure out is for a queen in some row, what columns is it in? So these variables here are telling you what column is the queen in row 1. So this is the set of 8 variables. And then you need to add a set of constraints that that's going to just enforce the fact that you can't have 2 queens attacking each other. The first thing you do is your columns have to be between 1 and 8. So queens actually have to be on the chessboard. Okay. You cannot have 2 queens in the same column. So all the columns have to be distinct. Like this could be, you could do this with like a very long Boolean expression saying x is not equal to 1, or q1 is not equal to q2 and q3 and so forth, but you get this nice function that does all of that for you, basically. So this is telling you that all the queens are in different columns. So at this point, all the queens are in different rows and all the queens are in different columns. You need to enforce the fact that all the queens are in different diagonals. That's what this part is doing. Essentially, what this is saying is that if Ing are distinct, you have 2 different queens, then it must be true, and these 2 things must be true, which basically saying that they're not in the left diagonal but the right diagonal. So this is written using an if, which basically means that if this is true, then your constraint evaluates to this, and if it's false, then this. I would probably write this as an implies. I would probably write this as I not equals j implies this, the same thing, but maybe a little bit more concise. And at this point, you have added all of your constraints, and you need values for all of your variables. This example doesn't use the solver API, or what's going on here. So for this queen, this tells you all the places where Qj cannot be. So this diagonal. Solve basically solves a set of constraints that you give it. So you add together this constraint, this one, and will give you values for all the variables that are involved in the constraints. Okay, so now this is the challenge for you. So you've got an equation here, x and y are integers. You want to get a solution for x and y. I think there is a unique solution, so that there's only one. And this is probably pretty hard to do by hand. So there's a template here. You declare x, something else that you need to do, and then you add some constraints and so the flag is the value of x plus 2 times the value of 1. So I'll give you a
And we'll post the slides so you can try this later, but I encourage everyone to try it out now.
I mean, if you want to install the
And make sure you guys install Z3-solver and not Z3
Z3 is like some other library. So uninstall Z3.
Did you just install it?
Pretty sure this is yeah, but like slide doesn't have to be at this point.
If anybody's having any trouble, I can come over.
Solve this. Because you can have multiple arguments, I suppose?
Yeah.
Oh.
They're just checking to make sure you don't make use of it.
Why is this argument for one instead of zero?
The first one is like the Nikhil, so it's very close. Like yeah.
For no, if they don't teach this shit with 220.
I mean, yeah,
What? Oh yeah, it's a char star type of way.
It was weird though. It didn't seem more match.
Does anybody have an answer? Yeah, all like every operator is basically overloaded in the most common sense way. So you can just use Python.
But I'm assuming not for exponentiation.
I think like star is actually exponential.
Right, but I'm saying the caret would still be that YSX star.
I think so, yeah. And I believe it would not even try, like it would just give up if you try to caret integers. Like I think it would just work on stuff that actually makes sense to do bitwise. I guess I'll also take questions right now if anybody. And then you have to go.
I think it's ZK solver. Oh, Is this working?
Yeah.
That's all.
Why are things names? Why? I think it's why. Oh wait, no, no, why squared. Yeah, that should be fine.
But like, is this model provide? Is this something the same?
I think this is well, yeah, the flag is x plus 1.
Okay.
Yeah.
No, there was a
Putting it in the format of like integer plus integer, you put in just like a total integer.
No, like the actual like answer.
Okay. Then
Yeah. Yes. Like actually, yeah, x.
Yeah, how do you do that?
All right. So okay, now the actual topic of this meeting. So why did I spend so much time on Z3 and stuff? Because symbolic execution, and particular Angr uses C3 for all of its like internal symbolic manipulation and constraint solving. So what is symbolic execution? Usually when you execute a program, like let's say you have a function with 2 arguments, right? Write something. So let's say you have like a function with 2 arguments, and this function returns x plus y. So usually you would actually give this some numbers as arguments, let's say these are integers, and it would give you a number out. With symbolic execution, instead of using real, actual concrete values, you use symbolic variables. So I would give this function a symbolic variable x, and you know what? Give this function a symbolic variable a, and symbolic variable b for x and y, and as a result, I would get a symbolic expression. I would get a plus b, which which is just a symbolic sort of expression. Like let's say this function was more interesting. Let's say this function did something like, if x is positive, it returns x plus y. If it's not, it returns, let's say, x minus y. Then what's going to happen is if I give it symbolic variables, when it gets to this point, you're going to have a split into 2 cases, depending on if A is positive or not. So if A is positive, it's going to return A plus B. And if it's not positive, it's going to return A minus B. So you can think of these 2 as like sort of forming some kind of tree. Every time you get to a branch point, you split. And for every location in the tree, you've got a set of constraints that need to be satisfied to get to that location. So to get here, A must be positive. And this is an example with actual code, like pseudocode or whatever. You can also do this on assembly. So the point is that, let's say I want a return value of like 15 from this function. I can then ask what should my inputs be. And that's a problem for Z3 to solve, because now Z3 knows what the output is in every possible case. You can code that in terms of constraints. And then Z3 can tell you, here's a model, here's a set of inputs that work. So that's basically what's going on here, except in assembly. So your input is in R1. X is in R1, looks like. And then you do something else and put the result in R3, and you check if it's 4. And then you want to find what should X be, what should the value in R1 be when you start. Then you get 4. The symbolic executor will go through each step. It will, everything will be in terms of symbolic expressions. So, like, let's say you give R1 the symbolic variable A. On the second line, it's going to store 3 times A. And R2, on the third line, we'll do something similar with that operation. And then you can ask, SMT solver like Z3 to tell you, okay, what could be. What this is used for, what we did just now is like a very simple example of reverse engineering. You can do this on much more complex stuff. You can, like the CTF challenges, we'll see an example of one where you basically have to do no reversing at all. You literally just plug in the program into Angr, you tell it, I want this output, tell me what input should be, and it will solve that for you. You can do automated exploitation. Again, in all of these problems, basically any problem involving a program where you can encode what you want as some kind of constraint, like my output needs to be this, or I need this value written at this place on the stack or something. That's a problem for symbolic execution. With research, you can use it more generally for binary analysis where you're not trying to solve everything with symbolic execution. You're maybe using it to extract some information from a function, gain some information about some part of the code. Okay. Or instrument the binary in terms of, you can do like breakpoints, callbacks, and stuff like that. Angr is a symbolic execution library for binaries. There's other stuff for like Python programs and JavaScript. And yeah, you can use it to automate ref challenges, binary ref challenges. Very easy to install. This is a template by Richard for the sort of challenge where you can basically just plug in the binary into Angr, tell it I want this output or I want to get to this state. That's my win condition. It will solve for your inputs. This is an example that you can try using that template. Very standard ref challenge. It asks you for some input. It does some checking and it tells you if it's correct. Okay, tips. So sort of when you have a lot of branching going on, or when you have a complex program, the states can get very complicated. We'll look at state explosion later, and that takes up a lot of memory. So you can just run out of memory. There's some things you can do to try to fix that. There's reuse Z3 solver, which will not split the solver at every state split. You can get it to try to merge states automatically. I mean, all of these, the root causes that when you have too many states, that's too much memory. And lazy solves basically tries to defer satisfiability checks. So for instance, like you might have some states that are actually impossible to get to. It's like if you have like an x greater than 0 in an if, and then like you literally have inside the same if x less than 0, you're never getting into the x less than 0, not possible. And Angr will try to use Z3 to tell you, are the conditions satisfiable to get up to that point? And if they're not, it will not try to explore. Yeah,
so Angr optimizes that out, not Z3. Like if Z3 were, because like Z3 would create the tree, correct?
Right. Or I guess, so Z3 is like the thing that Angr uses for all of its symbolic needs. Okay. So Angr is going to step through your program. So Z3 is, has no knowledge of your program necessarily. Okay. Angr has that knowledge. It's going to step through your program. It's going to tell Z3, and then at this point, I have a constraint saying x greater than 0 and also x less than 0. Is this satisfiable? Can I actually get to this point? And Z3 will tell Angr no. And then Angr will say, okay, I'm not going to, let's say there's like a function call here, right? Yeah. Angr will say, I'm not even going to try to go into that function. The problem with that is that that's a lot of pulse to Z3. And that takes memory again for a lot of states. So one thing you can do is set lazy solves, which will try to avoid these sorts of checks as much as it can. Sort of counterintuitive, right? But in practice, it actually ends up sometimes working with memory, saving memory, if you aren't constantly making calls to Z3. Okay, yeah. I think you want to add. Oh, did I? Okay. Angr internals. So what is Angr actually doing when it symbolically executes a binary? It uses Z3 for constraint solving, as we talked about. It has the responsibility of going through your program, telling Z3, if I have, let's say, an add instruction in assembly, you should put this plus this into this variable. We tell Z3 all of that, and then when it gets to branch, any sort of branch, like a function call or a like a compare and then a branch or something like that, it's going to split its states, something like that. right? And then associated with each state, it's going to add conditions based on the branches it does. So like, let's say you do some more branching at this point based on more conditions, that's going to get entered in to the path conditions. Angr manages its states through what it calls stashes, which are collections of states that have something in common. So let's say, for instance, you can have states that have some sort of error, maybe they are segmentation fault or something. It's going to put those in one collection, states that dead-ended in the sense that execution finished, there's nowhere to go. You can specify, you can tell Angr to find certain addresses or to set certain addresses as like targets. If it gets a state at that address, it will put it in found. And then you can have states that it can still do more execution on. Yep, correct.
Okay. Yeah. So it will. Do you have to add a flag, like an argument, to actually save these states, or are these states just saved?
Yeah. Some of these are done by default, like active dead-ended error. That's default behavior. For found, you need to actually tell it, okay, I want to find this address. You can also, customize Angr. You can make up your own stashes and control all of that yourself if you want to do that. And what actually controls how these states are managed between stashes and stuff, the simulation. The example go away. Let's see if I can find the solve script. How do I click on a link?
Escape.
Okay.
I think the example is it's on the side window. So.
Oh, what?
I mean, I'll just go there.
Yeah.
Okay, so this is an example from challenge at Boiler CTF, coincidentally. Okay, so this is, I guess, like the most basic way you can use Angr. So what you're going to do is you load in a binary here. So it's called Angr. You can set a base address if you want. It makes things easier for you with like offsets. You don't do it. Then you need to actually create some sort of symbolic input that you're going to solve for. So in this case, you want to know what input makes my binary print correct or whatever. You have to, so you usually have to figure out the length of the input because you need to know how many variables to actually create. And that you would usually do with like manual reversing. But once you have that, you can create that number of variables. You want the input to end in a new line. This is input to standard end. So you hit enter after you type in playing. And then you're going to create a state. This is a state that starts at the entry of the program. For the next state, essentially tells Angr to initialize as much as it can with like registers and memory. And then, I mean, that's basically all the, I guess, manual work you need to do. You basically add, well, yeah, I guess this is, I guess, sometimes if you don't do this, you might get solutions with like non-printable characters. So you want to make all the characters in the flag actually printable ASCII characters. You can add, so these are conditions that would get added to the path constraints of that state, and they would continue for every other state that sort of descends from that. You create a simulation manager to actually do the symbolic execution, then this line is basically where all of the actual symbolic execution is going. So Angr is going to go through the whole programmer is going to do all of the splitting and so forth. It's going to run through everything until there's nothing else to do. Maybe you've got some states that error, some states that dead-ended in the sense that nothing more to execute. So this is sort of looking at one of the stashes. You want to look in the dead-ended stash because you don't want the program to error out. And then you can ask the state what's in your output. And this is something Angr has kept track of as you ran this Symbolic. So project.dump1 is standard out. And this is, again, through like manual reversing integer or whatever, this is what you want the binary to print. So you check in which states is this actually printed to the output. And you then for those, you pick one of those states. Ideally, there should be just one. You want a unique solution. And then given the sort of constraints of that state, you ask Angr to give you there is a different way you can do this. That's what the template does. You can ask it to also, as it's running. So in this case, you're asking it to run execution until it cannot anymore. But you can also tell it while it's running, tell it what states it should be considering as found states and what states it should avoid. So if you know that you've got some condition if it's false, there's no way that's the right answer. Let's say you get like wrong in your output. You can tell Angr, don't even bother exploring that state anymore. If you've got states that it finds, you can tell Angr, don't bother exploring that anymore. You found what you need for it. And then you would go in the states that it found, and then you would ask for the flag. And well, so this is asking for the input, and implicitly in this line, what's going on is it's telling Z3 there's a set of constraints associated with the state relating to these variables. Based on those constraints, what the values of those variables. You can also just directly ask for the values of those variables, similar to the Z3 example. For the template.
On the left side. Trying to go back to the slides.
Yeah, it's on the side.
Oh wait, right.
Or slide shows at the top right.
So I mean, this sounds great, right? You can reverse without doing any manual effort. The problem is that it doesn't always work. Doesn't work because you can have programs where there's so much branching that the number of states is unmanageably large. Like you can have, there's an example on the next slide, but like if you have branching inside a loop, that's going to become a lot of states very quickly. You're going to run out of memory. You are not, you're going to run out of processor power because your computer cannot do all the calculations in any reasonable amount of time. So this is an example. So I've written this in a very specific way. I could have written this differently, which would not have the state explosion problem. But the way I've written this, you can plug this into Angr. It's going to take a very long time and take up all of your memory. So can anyone tell me why this would cause state explosion? Like what about this program is going to make the number of states very large? And if you know how many.
So I'm guessing, right? But buff is buff you're doing fgets, right?
Yeah.
So is this gonna be how many possible fgets, like any possible like valid fight, right?
Yeah.
And we got 26 of those.
Yes.
So is that gonna be like 256 to the 26th branches?
That's a good thought. That's a good thought. That's actually a good point. Angr has sort of hooks for a lot of C library functions that would otherwise just make things very bad.
Okay.
So Angr will take care of your FKs, no problem.
Okay.
So the problem is after the FKs. Like it is true that like it may be the case that in the source code of FKs there is some stuff that's going to be very problematic, but Angr has implemented all of this sort of stuff in like Python codes basically that replicate the behavior. Right. So you should focus on this loop. So what's going on in this loop?
Is it because you do the loop first and then you
Okay.
check if that's correct? So you have to do the loop every time.
Yes, so that's a part of it. So what's going to happen once you get into like once I get to this if, right? Once the symbolic executor gets here, what's going to happen?
I didn't see where you're pointing.
Oh, sorry.
It's gonna make a comparison. So
It's going to make a comparison and
create a different branch.
yeah. So each time you get here, it's going to split your states in two. And there's no way to actually get out of this loop early. If I had done something here, like if buff I not equal to target I break, then that state would not be explored any further, right? So that would be out of the loop and done, basically. But as it's written here, each time you get into this loop, the number of states doubles. And you're doing that 26 times.
I added a diagram.
Oh, okay. Right. Yeah. So, yeah, each time you get here, each state turns into two states, depending on whether that if succeeds or not. And that's a lot of states. And I mean, this is the sort of thing where it's not sufficient to just put your program through Angr and hope that it works. This example is easy enough that you can just do this by hand. There's nothing very hard. But imagine you had something like more complicated in this loop that you cannot do by hand. At that point, like some way I might try to fix this is I might add an avoid condition saying if the value of I and the value of count are not equal, you know that you're done.
Yeah, so can you automatically get around this by doing like automated binary patching to switch it to an equivalent statement that will break?
Right, you could do that. You could do that. That is, of course, one option. But there are, I mean, Angr is very extensible, very customizable, and you can instrument it.
Okay.
So you can be sort of very creative in terms of how you control how Angr runs through your binary. So for instance, like if you said, if I is not equal to count, then you put your state in a stash saying wrong.
Okay.
Right? None of those states are going to, or I guess, if you want count to be one more than I. But if you can make a comparison based on I and count, because each of these conditions is just the same. Right, so Angr's behavior, you can modify it, instrument it, you can do like breakpoints on like every memory read or every register write or something like that. You can control how Angr steps through states. So it's default, there's some default behavior. You can change that if you want. Like, let's say you want to do a depth first search instead of a breadth first search. That could be an example to your tree of states. Like you want to take each state, branch it out, and then go through each of those, branch those out, instead of going with one state till it dead ends. That's something you could do. I mean, you can basically get as creative as you want with this stuff. And the point I want to make is that with CTF challenges, you can often just plug in a binary and get an answer with no more effort. But as soon as the scale of the problem gets larger than a very basic CTF challenge, that's not going to work because of stuff like state exclusion. So you want to think of Angr as not just a tool for getting flags out of binaries. Think of it as something to gain information about binaries. It might be a flag, but it might also be, will this function ever return a negative number? you might want to do that by hand. Or you could tell Angr run this function and then ask C3 at the end, right? Or ask Angr to ask C3. Can the output be negative? In research, stuff like this is used. So there's a tool called Falseware, I believe, by people at UC Santa Barbara. What they are doing is so if you have a situation where a function takes a number and checks it against 5 different values, the number might be a 32-bit integer. There's a lot of possible values, but only 5 of them actually matter. So if you are trying to do some fuzzing or some like random testing on that function, you don't actually want to give it like values randomly sampled from whatever 2 to 32 values there are. You only actually care about those 5 values. And you can tell, or you can ask Angr, you can use Angr to infer from the function what are the values that it actually cares about. So that's in the sense of using it as something to get information out. Libmatch finds library functions in binaries. It doesn't even run Angr as a symbolic execution. It uses it only to do stuff like get function cross-reference testing. In that case, it's like a fancy keytree, fancy keytree to that. And yeah, so that's it. Any questions?
Yeah. So are there any open source, because it's very extensible, like exploit development things for Angr? Because I know in 2017, CMU had a big fancy auto hone thing, and this like that got to DARPA and it just disappeared from the void. And I haven't seen anything like that since. Is there like an open source equivalent that you know of?
I know Angr's documentation has examples on vulnerability discovery. In terms of like an actual like industry standard tool, I don't know, but they have examples on using it for stuff other than just reversing.
Okay.
So I think there are some examples that find
this was more like an I win button. Like there was like some reinforcement learning magic. We just passed a binary and it just computes. Yeah. It's like code born.
Okay. Yeah, I don't know if there's something like that. There is stuff on like some automated form on the docs. Anybody else? Okay. So
I just want to comment on Ronan's thing.
Yeah.
I did some research on this last year. The limits of Angr so far pretty much end at heap exploitation, which is most standard code at this point in time. So until Angr can solve heap exploitation, its value is quite limited in terms of real world usage.
Yeah. Well, I guess one thing that's important, like Angr's memory model is like a little iffy. So it does great with registers. It does great with concrete memory. As soon as you get to symbolic memory, it's very not good. Stuff like putting stuff at a memory address that is itself symbolic will be very difficult. Like I mean, in theory, if you put something at memory address X and then you do a load from X and nothing has changed, you should still get that same value, right? Yeah. And Angr should be able to figure that out. Currently, it doesn't do that. So, so doing stuff with like complicated memory magic is more difficult. Because that's one of the limits. That might be at work when you try to use it for exploitation. Any other questions?
You want to talk about the next meeting?
Oh yeah, okay. Next meeting. So boiler CTF been talked about tomorrow at 5 p.m. We don't know where we are meeting, right? Or if we are.
It's probably gonna be in Seabold.
This Sunday, location-based hosting with Angr. I have seen some of the slides. They look very cool. So the next Thursday, social engineering with Emma and Pablo. Yeah.
What Rainbow?
You'll see. You'll see.
Ask him. He's the expert.
You should Google that.
You know the guy that just is on TikTok and like somebody will have like
Just,
He plays like geo.
Yeah,
guess
he
so.
does, just a dual guess.
it's just location.
Agreed.